This is lecture 5D for Calculus 1 on the definite integral. So let's note right at the start that there is a big difference, a fundamental difference between the definite and the indefinite integral. The definite integral right here looks the same as the indefinite integral, only the upper and lower limits of integration are specified. You have the a and b, you have some values or some functions, you have something there at a and b. The result of that is a number, right? Unless a and b are variables, then you'll have something else. But let's let a and b be numbers, then you get a number out. The indefinite integral, okay, the result of that is this function, which is the primitive of f of x, of little f of x, specified up to the constant of integration. So the difference when this definite interval, we're going for a number. Now the definite integral can be evaluated three ways. It could be evaluated numerically as a Riemann sum of approximating rectangles. It could be evaluated numerically by some function when there is no closed form, when no closed form primitive can be specified. Again, what is meant by a closed form is some combination of power functions, polynomials, exponentials, sines, cosines, hyperbolic functions, logarithms. Some combination of the elementary transcendental functions and the power function. Right, that's a closed form solution. If you can't find a closed form solution, there are special functions. Some of them are numeric that apply to some integrals. These are published in certain handbooks, and they're more of a subject to advanced classes. But anyway, there's two numerical ways to evaluate the definite integral. There is an analytic way, and that is that you find the primitive and you evaluate the primitive at the limits of integration. All right, when we first started doing the integrals with the Riemann sums, we said that the integral was the area between the arbitrary curve and the x-axis, right? But sometimes it was negative. So the idea of using the area kind of makes sense, but you know, use the area, the word area, a little bit loosely. It could be positive or it could be negative. Here's what the fundamental theorem of calculus says in abstract. If I have some function little f of x and I'm integrating it from a to b, I find the primitive, capital F evaluated at b minus capital F evaluated at a. The result of this will be a number. Right. Here's an example. Say I have the function secant squared and I want to integrate it from 0 to pi over 4. I know the primitive of secant squared is tangent, so I write tangent here. Then I have these two limits of integration, and we use this notation that we did with derivatives. After you find that primitive, draw a vertical line. At the bottom of it, put the lower limit of integration. At the upper end of the vertical line, put the upper limit of integration. Then apply them. So this becomes tangent of pi over 4 minus the tangent at 0, and you get a number. Remember, all angles are in radians in calculus. So now I'm going to state several of the properties of the integral, and these help us evaluate integrals as much as knowing some of those elementary primitive functions. The first one has to do with adjacent intervals. If you have an integral all the way from a to c, you can break it up into a subintegral from a to b and then a subintegral from b to c. Sometimes this helps. Especially helps if it's a piecewise function. Okay, so I'm integrating from a to c. I can just go from a to b and add to it the result from b to c. Graphically, this just says that adjacent areas of adjacent subsections add up to the area of the section. So we can look at this also analytically to see if it holds. Here's the integral from a to b. To perform this integral, I find the primitive, which is f, evaluated at the upper limit, subtract the lower limit. Okay, so I've got f of b minus f at a. Then I want to take the next integral, okay, right like that. So to do that, I look at the primitive, evaluate it at the upper limit of integration, c, subtract from it the value of the primitive at the lower limit of integration, which is b. Obviously, f at b is going to cancel, and you end up with f at c minus the primitive at a, which is the integral from a to c. Sometimes this property about adjacent intervals is used in a different way. Say you know the interval all the way from 0 to, and I'm going to say x plus h, of some function f. Look what I've done here. I put nu, the Greek letter, here for the dummy variable of integration. Again, this is just a dummy. It goes away. Right, so it's just a placeholder. I guess dummy's not a nice word for it. It's a placeholder. All right. The reason I did that is because I have an x up here in the limit, and I don't want to repeat that x down here. That's poor form. Also, it's wrong. Right. So I just say f of nu d nu, and that's fine. All right. As long as I'm consistent. It's the variable I want. I change all of the x's to nu down here after the integral sign. Okay, so I'm going to go ahead, and what I'm doing here after that, I'm integrating from 0 to x plus h. Then I'm integrating from 0 to x. So I'm taking a big interval and subtracting off a little section of it. So what do I get here? I get the primitive. Evaluated at the upper limit, x plus h, minus the primitive evaluated at the lower limit. Now I go to the second term. Okay, I'm subtracting now. So I have the primitive evaluated at the upper limit, which would be x, and then I subtract with the negative sign again the primitive at 0. Right. All I'm left with, of course, is f at x plus h minus f at x. So that is the integral from x to x plus h. So I had a bigger outer interval and I subtracted a little section at the beginning of it. I end up with the other subsection. This next property of the definite integral has to do with the limits of integration. When we're thinking of those Riemann sums, we tend to think that we have an interval a, b, and a is less than b. There's no, and again, the idea of integral goes beyond the idea of area, right? And so just forget that for a while. All right, I don't have that requirement. So here's a, b. I could switch the limits of integration, just totally switch them around, and the result of that is that the value would be negative. That's because you're multiplying by b minus a. So if you switch out around and multiply it the other way, a minus b is a negative of b minus a. Okay, so again, this stretches the analogy that an integral is an area. It's not necessarily an area, it's beyond the idea of area. So if you take the limits of integration and you switch them, you put the lower one for the upper one and the upper one for the lower one, you can do that problem, but the answer will change sign. And from that, you can also get this result, that if you integrate from a to a, you really have f of a minus f of a equals 0. If you think of that in terms of the rectangle, that means the width of the rectangle is 0. So its area would be 0. The other that we've talked about before, the other property is that it's a linear operator. So if I integrate this function, I can just break this up into two integrals, break it up at the plus or the minus sign. The constants multiplying f prime or g prime, in this case I used f prime and g prime, can come out in front, and then you can take the integral. Right. Of course, like it says here, this is a very useful property since it allows us to compute integrals of algebraic combinations of functions when we know the primitives for each of the functions. Here's an example. I'm going to show it to you mainly because of the opportunity here to make a sign error. So I'm going to integrate this polynomial, x cubed plus 6x squared. All right, I could integrate each one independently. So x cubed, the integral of that is x to the fourth over 4. Then I take the integral of 6x squared, and that would be 2x cubed. Now I have to evaluate this combination, so I use that vertical line. I put the lower limit here of minus 4. I put the upper limit here of 2. Now when I plug in to the equation, I would plug in the 2 in this whole expression, so I get 2x to the fourth plus 2 times 2 squared. Now when I plug in the minus 4, remember this, you are going to subtract everything. So put it in brackets. If you don't put it in brackets, you can make a sign error. So I put whatever that lower limit of integration is in here and raise it to the 4th power divided by 4. And then I put the lower limit of integration here, and that should have been cubed. I'll fix that. Right here, this should be a 3. This should be a 3. I'll have to complain to the person who made these slides. Okay, there we go. All right. Now look where I put all that in brackets. The reason I put it in brackets is because I have to subtract all of it. I have to subtract all these terms. So that's why I'm saying that you have there's a tendency or a propensity here to make a sign error when you integrate over a polynomial or any combination. Remember, at the upper limit you evaluate, at the lower limit you subtract the whole function. We can use the global max and the global min of the function to obtain an upper and lower bound for the value of the definite integral. So let's say f is greater than or equal to some number little m, and it's less than or equal to some number big M. Then I know that the integral from on a to b, then I know the integral of the function on a to b is another property of the definite integral is that we can use the global maximum and the global minimum of the function to get an upper and lower bound on the integral. Let us say that f is, let me get the marker here, f is greater than or equal to some value m, and it's less than or equal to some big M on the interval AB. If I take the integral of the function on AB, I know it has to be less than big M times b minus a and greater than little m times b minus a. Where we get this result is we can, if we integrate a constant, here's a constant m, and I'm integrating m, in this case the little m, the lower, the global minimum, then the m comes on the outside. The integral from a to b of dx is x, a value between b and a, and that gives me the result. You can also use this to see if the integral is going to be greater than 0 or less than 0 too. Here's a graph showing that comparison test. The red line is the function, which was x squared plus 4. The function, the minimum value for the function here is 4, maximum value is 31. So you can see the integral, the area under the curve of this function would be this, all of this plus down to here. Of course, it is greater than just this by itself, which would be little m times b minus a, and it's less than all of this area, which is big M times b minus a. In fact, you can use this. Say you wanted to compute, you only wanted to compute the area here. You could take the integral of m over this, which would be 3 minus 0 times big M, 3 minus 0 times 31, will give you all of this area, and then you could find the integral of the function here and subtract it, and all you'd end up with is the area between 31 and the curve. Symmetries are used in integrals to simplify the integration. If you have an even function and you're integrating from minus a to a, you have to be integrating on an interval from minus a to a so that 0 is in the middle of it. Okay, you can break this, of course, into two pieces. One from minus a to 0, and another from 0 to a. They're going to be the same, so all you have to do is half of it and multiply by 2. If it's an odd function and you're going over that same minus a to minus a, then remember they're going to be opposite signs, and the answer will be 0. I'll show you a graph of that now. Here's an integral from minus 4 pi to 4 pi of the cosine. Cosine is an even function. So if you see here, every blue area, which would be right here, is matched by a corresponding orange area here. They're the same. The area in here is the same as the area here. The area up here is the same as the area up here. Because I'm going from minus 4 pi to 4 pi, all I have to do is half of it. For example, go only on the blue, what's shown in blue, and that would be the answer. Multiply it by 2. Here is the integral of sine x over the same, minus 4 pi to 4 pi over the same interval. But you see, because it's an odd function, every area that I have here has an opposite area down here. This one is here, opposite up here. We have this one, we have one with the same but with a negative sign here. The result of this is 0.